Hello and welcome back. This is Greg French. Today we're going to begin lesson 3 of our 3 lesson course here for building a small obstacle avoidance robot. And this was designed in SolidWorks and then printed using the STL files that we created, then converting them to a G-code and printing out all the different parts. Then we went in the last lesson 2, we went ahead and mounted all the electronics, the battery holder, the breadboard, the little ultrasonic sensor, and the Arduino. And today we're going to do the wiring and the coding to get it to run. So let's begin lesson 3, wiring, coding, and obstacle avoidance robot. The objectives students will learn, again, working in teams, this time teams of 3. I actually prefer 2, but teams of 3 sometimes work too. How to wire, code the obstacle avoidance robot using the wiring diagram and the Arduino IDE, or integrated development environment. That gives you a little development environment where we can do the C coding. Parts needed: we're going to need the robot chassis and all the parts that should have been installed on it. We're also going to need some jumper wires because we're going to wire this up. Here's a little fritzing wiring diagram that I created. I'm showing a Uno Arduino instead of the Nano, but it's pretty close to the same thing. We still have the digital pins up here, and then down below here we've got the 5 volts and also have a ground. I'm using the ground up here, so the one down here, but any of the grounds is fine. You want to hook up your battery. And here we're using a little bit larger breadboard, but we're running the negative down this whole strip, because on these little larger breadboards, these rails actually can be used for your power rails, and that negative actually starts here and goes all the way the full length, and then the positive the same thing. The inside of the breadboards, like the little nano or the smaller breadboards, with just these 5 are connected together in rows of 5 instead of having that whole rail connected. So we connect the battery to positive here. Now you notice on our servos, the red is also connected to that positive rail on both the servos, and then the negative on the servos is also connected to the negative. So the servos are directly connected to the battery, which is what you want. You don't want them connected through your Arduino, because you can overload the Arduino if the servos draw too much current. The little ultrasonic sensor has 4 connections. We've got VCC here on the left, and you can see that's what connected with the red wire to the positive, and then the black is the ground on the far side. Then we have a little triggering and echo signal here, so the triggering is coming up with a blue wire connected to actually we're going to use 12 and 11, so it looks like it's connected to 11, and then 12 for our other signal. Now the servos are going to be connected to 9 and 10. So, and you can see here our servos do have control signals connected to 9 and 10. So our control signals for our servos, our control signals, or our trigger and echo for our little ultrasonics, and all the positive and negatives, and that's about it. The wiring is actually pretty simple for this. Again, we're just going to substitute the Nano in for this big Uno. Uno is normally what most everybody uses with the little robots, but this robot that we're creating is so small, the Nano actually works a lot better. Up in here, the notes servo are connected directly to the battery. That again prevents overloading the Arduino circuit. We're using 5 volts, and the ground, which on the Nano is on the bottom here. Here's the 5 volts. We're using the ground here on the top, but we also have another ground on the Nano down here that we can use. Digital pins 11 and 12 for the HCSR04, that's the ultrasonics, and then pins again 10 and 9 for the servos. Down here we've got some coding. We're going to use the Arduino IDE program, and we're going to upload the obstacle avoidance code as we create it into the robot. Note, install the Arduino program. To install the Arduino program, make sure we have Nano selected. So we'll come over here to your Arduino program. You have a little Tools tab. Click on that Tool tab. This opens up. We want to make sure we have the Arduino Nano. If it doesn't, just click on it. Select the Nano. Then up here, we want to the port. Select the port. We should be This one's COM8, but oftentimes in this information on the side here, you'll see Arduino Nano is what's been identified. And generally, if you have the driver installed, it'll automatically find that port and connect on your computer. And it's generally not going to be COM1, might be COM3 or a higher number port. But it's important to have that port number identified properly, so we're connecting our Arduino to the computer and we can program it. We can also open up our serial monitor, which is in this tool selection 2. If you click on the serial monitor, another window will open up, and that'll show you any detection that ultrasonic sensor detects. And in our program, we've actually got it so anything less than 40 centimeters will be detected, and that's what drives our program. Let's look at the program. Before we look at the program, let's look at this is a parallax servo. I like the parallax servos, and they have a pulse width here, 1.3 milliseconds, separated by another 20 milliseconds. So we get a pulse every 20 milliseconds and has a duration of 1.3. Now, as the length of the pulses decrease, actually they're going to be decreasing from 1.5 down to 3. What's going to drive that servo? So we're only reducing that pulse with about, 0.2 milliseconds, which drives it in one direction. Now also, if we increase that signal to 1.8, we'll drive it in the opposite direction. So we're just varying the width of our pulse, which is going to be detected by the servo and then driving the servo either clockwise or counterclockwise. And this is a continuous run servo. So this servo is not going to just go 90 degrees. It's going to continue to run either clockwise or counterclockwise depending on the width of that pulse. Hopefully that makes sense. We use just 0 and 90 and 180 to drive the other servos, but the parallax, we actually use these microseconds to drive it. I like the parallax. It's a very reliable servo, and it is available at parallax.com. Testing the robot with the function of the code and make any needed changes. So this is kind of one of the more difficult parts. We're actually going to have to try to test the robot, coding it, testing it, make sure it's going to be operating properly as a little autonomous robot. PWM is our pulse width modulation, which drives our servos. We also use the little nano to drive our quadcopters too. And we'll probably be making up some more lessons or videos on how to control a quadcopter using a little Arduino, because it's one of the contests that we've been involved in, driving an Arduino in a search area to take pictures and get GPS locations of survivors. So this is used to drive the servo speeds and directions. The parallax uses that 1.5 millisecond pulse with a plus and minus 0.2. So if we subtract 2 from that, we get the 0.3. If we add to it, I guess we get the 0.7. And then these run every 20 milliseconds to control that speed and direction. It says as the length of the pulse decreases from 0.5, the servo will gradually rotate faster in that clockwise direction. So as you decrease your pulse width from 0.5 to 0.3, you're actually going to speed it up as the closer you get to 0.3. Likewise, as the length of the pulse increases, in the opposite direction of rotation will occur, and as you increase it closer to 1.7, the speed will increase. We use delay times to adjust for the larger or smaller turns, because as we send signals to these servos and we drive them in opposite directions, the little robot will actually pivot in place, and you want to put in a delay signal so it doesn't pivot too much, but it pivots just long enough to maybe make a 90-degree turn. We'll talk a little bit more about that. We're going to use in 4, we're using the ultrasonic sensor to adjust the code and timing to allow the robot to successfully navigate the maze. We're going to use if and else programming statements, and algorithmic functions also can be used to make the robot decisions for the decision making. Let's look at the code. This is some code that I've created. I've actually used other people's code and just changed it and created my own code. we defined some triggering pins up here for our ultrasonic sensor, the trig pin. I'm putting on pin 12, and I'm defining the echo pin for pin number 11. I'm also going to put some LEDs in a later lesson. I want a little stop lights and headlights that would either come on or off as the robot is traveling. When it's moving forward, I was going to have some headlights come on, and as it detects an object, I was going to have some taillights come on. That'll be probably another lesson. We're going to include this servo library, servo.h. This is a library of functions that have been created in order to drive these servos, so they don't have to code that. We have on the servo, we're going to have a left servo and a right servo, so we got two different servos, and we're going to identify the two different servos with different variables. We have two parts of our code here. We've got a setup, and it says void setup, and a loop. The setup is just to identify these the triggering pin as an output, and the echo pin will be our input. And then our LEDs too, which we're not using right now. Servo right is going to be attached to pin 9, and then our servo left, we're going to attach that to pin 10. So this is pretty straightforward for our setup. The loop is where it gets a little more challenging, but again, this code is really simple and straightforward, so we shouldn't have any problem. Long duration distance, we're setting digital right trig pin low. Going to drive it low before we actually put a signal on it. And we're going to delay that we're going to delay this in microseconds, and we're just putting a 2 on that. And then we're going to digital right trigger that pin high so that we get a signal coming out that we can detect as an echo. And delay the microseconds. This removed from the line. I've got these gray lines. You've got 2 slashes here and this words here behind it. This is coding notation. It's very important to put this in your code so that when you come back later and you want to try to either maintain it or make adjustments to it, it's easier to identify what you're doing in the code. And also, if you want to remove some of the code, you can just put a couple of slashes in front of it, and that way it grays out and it's not going to be recognized by the program. And we have another delay in microseconds down here of 10. We're going to add this back in, and that'll be triggering it high, and we'll have that running for 10 microseconds, so we get a pulse coming out. The next, as we continue on with this, you can see we still have a long duration. We came down here, this is where we ended, and then we're doing the digital right. This time we're driving it back low again. The duration of pulse, echo pin, and high distance duration. We come down here, servo right in microseconds. Now this is where we're using the microseconds to drive our servos either in one direction or another. Now I've got 1550. Now 1500 is what it would normally be in the neutral position, and you can adjust. There's a calibration procedure for adjusting the servos. There's a little hole in the servos and a little pod or potentiometer in there that you can adjust to calibrate the servo, so when you have that 1500 on there, it's not moving. But what I did is I just put in 1550, and I found that that would keep the servo at a null. And then for the other servo, I put in 1535, and that nulled the servo. So these are my new null numbers instead of the 1500. But again, you could just use a screwdriver and adjust those servos so that they stop moving. Now the servo right 1300 is full clockwise, and then servo left 1700 full counterclockwise. So this starts driving the robot, and it's full speed. If it detects, I've got an if statement in here, if it detects anything less than 40 centimeters, now this is where I was going to have the LEDs turn on and stop the servo, because we write a digital right, LEDs, we're not running the LEDs, but the servo right, we're going to go ahead and stop it, and the servo left, we're going to go ahead and stop it. So if it detects something, we're going to pause it, and it's going to be paused for 2,000 milliseconds or 2 seconds. And then we're going to do a servo right. I just put 0 in here, and servo left 0. Instead of using the microseconds, I'm using a little different command or a little different function, and I'm putting a 0 in here and a 0. This will cause both of these servos to run clockwise at full speed, but we're only going to run it for a half a second or 500 milliseconds. This should turn the robot about 90 degrees. you might have to change this 500, either increase it a little bit or decrease it a little bit to change that 90-degree turn, because you want a pretty much 90-degree turn, nothing more, nothing less. So you have to kind of play with this to get that to do that. And then after that turns, I went ahead and put those neutrals in there, the 1550 and the 1535. This will stop the servos, and it'll pause for half a second before it starts running full speed again. And you can vary this code quite a bit to get the servos to do different things, to make it operate a little bit differently. Now, this is pretty simple. It's only going to pivot in one direction. So if it's a simple maze, this is enough code to get it out. As we make the maze a little more complicated, a little more challenging, that's going to be adding to this code quite a bit. So this can become a pretty good challenge in coding, depending on the maze. Down here we got else. Again, we've got the else statement to run these LEDs, which aren't even hooked up. And then if now we've got down here this out of range. If you see down here, we got the serial dot print. This is what actually gives you in your little servo, or that serial monitor window, gives you the numbers, which will be the numbers that it detects for the objects. And as it's detecting objects, as they get below 40, which we have up here in the program right here, this is where the commands start, and we actually get the robot to do something. So the robot ultrasonic sensor will be detecting objects at a pretty good distance, but until that object gets below 40 centimeters, the robot's not going to do anything. And you might want to adjust this 40 centimeters depending on the maze. If the maze is smaller or larger, you might have to increase or decrease that minimum distance that is detected. And you can see, looking at that serial monitor, what those distances are when it's either out of range. If it's out of range, it's not detecting anything, you'll get this. If you're greater than about 200 centimeters, you're probably beyond the ability for that sensor to detect anything. Well, that's it for the code. I'll probably be adding some future lessons as we create more challenging mazes and as we develop more code. But right now, this is the end of that third lesson, and with what I've given you so far, you should be able to create this simple obstacle avoidance robot that will be able to navigate a simple maze and get out of it. I hope you got something out of this, and I look forward to making some more lessons. Thank you very much for watching.